Good morning to all of you. Myself, M. Ramarao, Secretary, IGS Guntur Chapter. This is the 35th webinar of IGS Guntur Chapter, organized by IGS Student Chapter, Kids Engineering College, Guntur. IGS Guntur Chapter established in 2003, organized a number of seminars and workshops, significant being IGC 2009 National Conference, held at RVR and JC College of Engineering, Guntur. I am thankful to Mrs. Mary Teresa Hartzman, Technical Manager, Husker Asia Pacific Private Limited, Singapore, to accept to deliver this webinar lecture, Geosynthetic Encased Stone Columns. Before introducing the speaker, few announcements to participants. I request all the participants, please stop your video. During the lecture, you are going to chat with the host only, and you may chat audio and video issues only. Please do not share your information and questions. Question answer session at the end of the lecture. After completion of the lecture, I will share Google Form link, and its purpose is sharing PDF content of this lecture and your feedback, and question answer session at the end of the lecture. Our next webinar at 11 a.m. on 1st, that is Wednesday, by Dr. Manish Gupta, Joint Director CSMRS in New Delhi. And the title of the webinar lecture is Use of Geosynthetics in Water Resources Sector. Now I request Mr. J. Nagamohan, Assistant Professor and Advisor to IGS Student Chapter, Kids Engineering College, Guntur, to introduce the speaker. Mr. Mohan, please unmute yourself and introduce the speaker.
Sir, am I audible, sir?
Yes, fine.
Good morning, everyone. Hearty welcome to all participants to today's webinar on Geosynthetics Encased Columns, organized by IGS Student Chapter, Department of Civil Engineering, KKR and KSR Institute of Technology and Sciences, popularly known as KITS Guntur. Now, I would like to thank Dr. Ramarao Garu, Secretary IGS Guntur Chapter, for his support in organizing this webinar. I also thank Dr. N. Ravindra Krishna, Professor and HOD, for encouraging us in organizing this event. And now I'm glad to introduce our guest speaker, Ms. Mary Teresa Hartmann. She was born in Germany on 2nd April 1989. She completed her post-graduation from Ruhr University, Germany. She is working for Husker Group with various designations since April 2013. Currently, she is the technical manager for Husker Asia Pacific Private Limited, Singapore. To her credit, Mary has 6 publications. She is a recipient of traveling scholarship, Just Burger Medal, and member of Geotechnical Society Singapore, German Geotechnical Society, and International Geosynthetic Society. With this brief introduction, I would like to invite our speaker, Ms. Mary Teresa Hartmann, to start her presentation.
Thank you very much, sir, for the kind introduction. I'm honored to be part of this webinar series and to present to you today on geosynthetic encased columns. Okay, we heard enough about me already, so then I would like to start to show you the outline of today's presentation. It's comprising of 4 parts. First, I would like to give you a short introduction and the motivation of soil improvement and geosynthetic encased columns. After this, we will go into detail into the design and construction. So we will look at the construction process and the equipment, as well as the working mechanism and also the design principles. In the end, I would like to show you some case studies from land reclamation as well as road embankments. I think the motivation is very obvious for all you working as geotechnical engineers, with increasing demands of infrastructure facilities like roads, railway lines, harbors, as well as airports. We have to build very often in highly challenging areas. And then our aim should be to enhance the safety against failures for ultimate and serviceability limit state issues, like you can see on the pictures. So these are really normal conditions, what you can see on the left-hand side, which is not very uncommon for our daily business. So when we look into detail in soil improvement, what is the aim exactly of soil improvement? And this is, first of all, the prevention of slope failure, as well as the prevention of vertical settlements, as well as horizontal deformations. Secondly, we also want to reduce post-construction settlements and post-construction deformations, which can lead to serviceability limit state issues in the long term of our project. Also, another topic for extremely soft soil we would like to prevent is also the extrusion. What you can see on the top picture on the left-hand side, for example, this is a very nice example of extrusion. This geosynthetic tube has been placed on very soft seabed subsoil, and this soil you can see on the right-hand side was basically the soil which has been extruded below the topic and laterally deformed to the sides. On the right-hand side of the slides, you can see what happens to an embankment with no soil improvement. So it will settle over time, which gives us the characteristic settlement curve. And also we will be able to discover lateral deformations, which can decrease the use and the serviceability of our structure. And therefore, the geosynthetic encased columns, or shortly GECs, can be one very advantageous application to reduce or to improve very soft subsoil. What you can see on this slide is actually the system components. So you can see that the system comprises of the granular columns. This can be a sand column, a stone column, or even crushed stone column, encased with a reinforcement sleeve. On top of this, there is a working platform and a horizontally arranged basal reinforcement, which is normally a high-strength geosynthetic woven. This woven supports the load distribution from the embankment loads as well as the traffic loads, and help to distribute them to the column's heads. And then the loads can be transferred into the bearing soil. This end-bearing soil leads us to our basic assumptions, which are, as said before, this is an end-bearing element, and which is very important is that this system is not settlement-free. Another assumption is that the column fill is incompressible and that we will have equal settlements of soft soil and the geosynthetic encased columns. We will see this later again. So all those assumptions will bring us to the basic working mechanism of this system. So if the column is loaded vertically, it will settle, and due to the column fill being incompressible, the settlements will be transferred into a lateral expansion, and this expansion will lead to an activation of tensile strength. With adding more load, this will also then result in new settlements, a new expansion, and a new activation of more tensile strength. So this is the entire basic working mechanism of the system. Then all of you know there is a big range of different soil improvement techniques, starting from soil replacement, which is quite common for shallow soft soil layers up to 3 or 4 meter depth, then the vibrostone column and any kind of rigid bearing element like concrete piles or cemented stone columns, for example. So what is the big advantage of our GEC, the ring track column? And this is really when we look at our soil conditions, like on this graph on the right-hand side, we can see that the ring track column really gives the biggest benefit for extremely soft soils with undrained shear strengths less than 15. So this area which is highlighted here. The other systems will then have disadvantages like risk of tilting or bulging, or also the loss of fill material. The system has been developed almost more than 20 years ago by a contractor, by a geosynthetic supplier, as well as a professor in Germany who developed the design procedure. And therefore, in the last decades, the system has been used for roads embankments as well as railroads. It has also been used for land reclamation and even for bridge approach embankments to relieve the stress on the rigid piles. Today, we would like to focus on the road embankments and the land reclamation projects. But in general, the system can be also used in those kind of applications and already have been used successfully. So why does this system have advantages in extremely soft soils? And this can be stated is because of the encasement. So the encasement really helps to ensure the integrity of the column. So even if we do not have any lateral support from the extremely soft soil, there will be no loss of fill material. So the shape will stay as it is, even for soils with undrained shear strengths less than 15. So the minimum undrained shear strength the columns have been installed was 0.5 kPa, which is basically really thick water or really muddy sludge. And also for organic soils, the system can be of great advantage, as even for peaty soils which will decomposite over the service life of your structure, and the lateral support will be lost, the fill material is still nicely protected in the encasement. And the encasement, or this geosynthetic sleeve, also helps as a mega drain element. So all of you, like you can see on the left-hand side, know the effect of prefabricated vertical drains, which are drain radius of 50 mil. And you know that this already accelerates the consolidation significantly. And now you can imagine what happens if you bring a 40 mil, 400 mil drain radius element into the subsoil. So this will really accelerate your consolidation process. That also means all settlements which are required to activate the forces, like I've shown you at the beginning, can be compensated during construction. So the settlements will happen, but they will happen early, and therefore you can compensate this during construction. One part which has also been studied recently is the ductility of the system, because we work with soil and with a flexible geosynthetic. It's a very good performance also under seismic load, but this is not focused today. So what is the main characteristic or system features of our encasement, or of the system, of the column itself? And the first part is obviously the encasement. The raw material can be either polyester or PVA, polyvinyl alcohol. Many of you are familiar with PVA due to the good chemical resistance and high pH values. But also for this system, it's a stiffer raw material than polyester, and therefore we can achieve less deformation and less settlements by using PVA rather than polyester. But normally the polyester type is working pretty well in the common applications and projects. The sleeve can be produced with ring tensile strength up to 600 kilonewtons per meter. And this also relates to a radial stiffness of up to 6,000 kilonewtons per meter. The great advantage of the geosynthetic sleeve is that it can be produced with no seams. And this means there are no weak points which can break. And also we have equal stiffness all over the circumference. So this is the big advantage of a circular woven material, that there are no seams and therefore no weak spots in your fabric. The other part of the column is of course the fill material. So there are some basic criteria that it should be, for example, 10 times stiffer than the surrounding soft soil, and the friction angle should be larger than 30. And also it should be a granular and highly permeable material due to the effect of the mega drain we have talked about earlier. The advantage is also that you can use sand, gravel, and also crushed stone. And therefore, you can use any material which is locally available, which fulfills these criteria. So in some projects, when you have a sand source close by or a gravel source close by, this can also give you a significant reduction in transport and also material costs. The dimension of the columns, the diameter can be produced between 0.4 meters and 1 meter, but normally the standard diameter is 800 mil or 600 mil. Due to the weaving process, the encasement will be produced with an infinite length, but the longest columns which have been installed so far had a length of approximately 30 meters. The second part of the system, besides the column, is the basal reinforcement. So this lays in the working platform or in the load distribution platform on top of the column heads. And this is a high strength woven typically, which can be also produced from polyester or from PVA. In generally, it can be produced up to 2,500 kilonewtons per meter. But normally, the normal applications vary between 400 and let's say 2,000 kilonewtons per meter. And this is a big advantage when you have those high strength materials, that you have a single layer reinforcement system and therefore a good load distribution between two layers. And also in terms of workload, it's much easier and saves the construction team much time if you only have to place one geosynthetic layer instead of two. The functions again, the basal reinforcement on top of the columns improves the load distribution. It also separates the soft soil from the embankment fill. This also gives you costs benefits because you can save your high quality embankment fill. The basal reinforcement enhances the slope stability, and it also takes the spreading forces. Normally, the width of the material is 5 meters, and the length can be produced depending on the weight for shipment, or also can be customized to reduce any cutoffs. Then we are already jumping into the installation. I know this is the part many of you are waiting for. So how can this be installed? And therefore, I would like to show you the displacement method, which is the most common installation method. What happens here is that you need to have steel encasement, which is used temporarily. It has a closed end at the bottom, which is driven down with a rig and a vibrator. Due to the closed bottom, the soft soil will displace and squeeze laterally. After you have driven down the steel pipe, the encasement textile will be placed inside, and then the sand can be filled. When the sand is filled up to the top, the encasement, the steel pipe, can be withdrawn under vibration. And then the flaps at the bottom, which are movable, will just open, and then you can remove the steel pipe, and the sleeve with the sand will stay inside. And here again, you can see that the column needs to be installed down to the level of a bearing element. So we must not forget that this is an end bearing element. Normally, the columns are recommended to be installed in a triangular pattern, which provides the best load distribution. And I already mentioned it, the standard diameter is around 800 mil or 600 mil, but this also depends on the available equipment and on the available size of the steel pipes which are used for the installation. But this 800 mil diameter columns have shown the optimum of the required number of columns and the installation speed. So that is a good value to start your considerations from. The area ratio, the replacement ratio, is normally between 10% and 20%. And this shows also the significant difference between vibrostone columns. So when it becomes really, really soft soil conditions, for normal vibroflowed stone columns, the area ratio goes really up to 30 or 40%. So normally by using the sleeve, the number of columns can also be reduced compared to the use of normal stone columns. I brought some videos and I hope they will run smoothly now. So this is the moment when the rig and the vibrator bring down the steel encasement first. Maybe I will show it a second time just to make sure that everybody has seen it properly. So this is the steel pipe. The flaps at the bottom of the steel pipe are closed, and therefore a gap is created. And then going to the second video on the right-hand side, that shows that the geotextile is put into the empty steel pipe, and then normally a kind of this adapter is used to place the sleeve inside. Maybe I show it a second time. If the software let no. Excuse me. Ah, okay. Okay. After this, when the geotextile is placed, the sand or the granular material can nicely be filled with the use of a normal excavator. And then normally you use a kind of a funnel, which just supports or eases the filling of the material. When the sand has been filled up to the top, this belt is loosened and also the adapter is removed, and then the vibrator can withdraw the steel encasement. So summarize what you need in terms of equipment is basically a vibrator and the basic carrier, the steel pipe with length depending on your soft soil depth, then the funnel, which can be quite helpful, also the wheel loader to place the funnel as well as fill the soil material, and then what you can see in the back of the picture over here, this is the GECs which have been cut to the length which are required depending on the soft soil layer depth. When the geotextile encased columns has been installed, a working platform or a transition or a load distribution platform is placed, and also the high strength geotextile is unrolled. So this can be simplified with an installation like this installation frame, and then it can be easily unrolled. To protect the geosynthetic against wind, normally just a sand pile is placed to load it. Just for your background information here, this is, for example, a geotextile woven with an ultimate tensile strength of up to 1000 kilonewtons per meter, which has been used in this project. The textile normally needs to be covered within a day to give a good UV protection. And this is normally made with this end tipping method. So whenever possible, the direct driving on the geotextile need to be avoided. When the design requires also a wraparound is being installed, that means that at both sides of your embankment slope toe, the geotextile is lifted and then wrapped around and back anchored. This gives you a nice anchorage and also helps to reduce the lateral deformation in your embankment. In order to show you the working mechanism, we look at this real scale test. This is, for this test, in total 10 columns have been installed, and the design was made with a factor of safety of 1.0 to provoke actually failure. So the test was about finding the failure mechanism of the system. So the trial load was made by 3 containers, and during the loading it was realized that there was no sign of failure, and therefore they added even some soil bags to increase the load on top. But still they saw some cracks in the working platform and some settlements, but it was no rapid or dangerous failure, so it was nicely predictable. What they also did in this trial was to measure the stress on top of the column and the stress on the soft soil. And here you can nicely see that by increasing the load by the containers, also the stress on the columns and the stress on the soft soil increases. What you can also nicely see in this trial is the fact that we said we will have equal settlements on top of the soft soil and on top of the columns. And this has to be, this happens due to the arching effect or due to the load distribution, so that we have much more stress on top of the columns compared to the stress on the soft soil, which can be summarized as that we will have a significant reduction of vertical stresses on the soft soil, which later brings us to smaller settlements of the soft soil and also to smaller creep settlements, what we will see later as well. If you are interested in doing a design, you have to consider 3 different parts. It's first of all the vertical design. This ensures sufficient tensile strength in ring direction, so that basically your sleeve is strong enough that it won't break. And you will also estimate the settlement of the GEC improved area. The second part would be the so-called horizontal design. And this is the slope stability, so the global stability of your embankment slopes, and also you estimate the sufficient strength of the basal reinforcement. Finally, you also do a time settlement analysis to analyze the construction time and also to help with the construction schedule. So very often the geosynthetic encased columns and the embankments on top are installed in with filling periods and waiting periods, wait for the excess pore water pressure to dissipate to ensure a safe construction. And then the next construction step follows when excess pore water pressure has dissipated. If you're interested in the design guidelines for the horizontal design, there are many national codes available. I just gave you an overview of some designs from Europe, but the only design guideline dealing with the vertical design, so really with the design of the geosynthetic encased column, to my knowledge, is the German code, which most of our designs also is based on. Maybe I will just, yeah, so the design principles are shown on this slide. So it's the unit cell approach accordance to Reitel. So this is actually based on the normal design of vibro replacement columns. So we're looking at one unit cell comprising of the influencing area and the column itself. Then we talked about the arching effect. So this is again what we have seen in the trial already, that we have the load concentration on the columns and less load on the soft soil. When we make a cross section through the unit cell, we see actually the drawing on the right hand side. So here we can see the load distribution talked about earlier, high stresses on the column and low stresses on the soft soil. The vertical stress on top of the column will be the vertical stress on top of the column will be transferred into the horizontal stress, and you can see that the horizontal stress inside the column is much higher than of the soft soil, and this difference, this is taken by the geotextile encasement. So this is what our encasement contributes. It gives extra stresses to the system. And this is also what we have seen here. This clearly shows the results or stresses that the results we have observed in the trial field are correct. For the design, the tensile stiffness of the material you are using is the main parameter which is required from the geosynthetic encasement. I will just, okay, sorry, I had a note at the chat and I was, okay, but now I'm back again. So the first case study I would like to show is in highway embankment in Poland. It was in Highway A2. And the soft soil was characteristic as really low bearing organic soils. The project requires the column length of 30 meters, which is so far the longest column which has been installed. And there were high restrictions in terms of the allowable post-construction settlements, which had to be less than 10 centimeters, and the allowable long-term settlements, differential settlements would be less than 15 mil every 10 meters. And here you can see that they have worked with 2 different rigs, and this also can give you a good time optimum when you can work with 2 rigs. And what you can also see that they had different steel pipes on site already. So whenever they move to a place with less thick soft soil layer, the steel pipe could have been chosen accordingly. This is the typical cross section or the longitudinal section showing you the layer of the soft soil from PT organic soils. And then there was a working platform installed and the columns in those yellow lines. This project also gave us great insights in the working mechanism of the column, because a lot of instrumentation has been installed. Like you can see some strain gauges and also some strain gauges in ring direction. And this picture also gives you a good idea of the scale of 30-meter long columns. So this was really a very great challenge to install the columns in that depth. This is a picture from the basal reinforcement, again, to protect against winds. Just sand has been used to to load the textile before the working platform was being installed. And you can also see some installations which also has been used for monitoring. Giving you an idea what has been analyzed with the ring direction, just very short. This draft on the right-hand side gives you the change of diameter in percent over the column depth. So the points show you the place of the strain gauges. And this is what I have also showed you at the very beginning. I talked about the expansion and the activation of forces, and we can nicely see that the column indeed expands, and therefore forces can be activated in the column textile. And here again, the earth pressure has been monitored on top of the GEC's heads and on top of the surrounding area. And also here we can see the characteristic load distribution, which is basis for the design and also for the working mechanism. This is just one picture from after construction. So the construction went really nicely, and it was great success for us, especially because we also could gain that much of information on the working mechanism and also behavior of the extension laterally. The second case study I would like to show is one of our, I think, biggest projects ever done with geosynthetic encased columns. In total, over 60,000 GECs have been installed with a length of 40 meters and a diameter of 80 centimeters. This is the Airbus facility in Hamburg, where they used to build the A380. So it wasn't possible to find any place in Hamburg to build this facility, and therefore it was decided to extend their facility into the river Elbe. And you can imagine these are all marine clays and sediments and very organic sediments. The construction was a great challenge, mainly because of the undrained shear strength of 0.5 kPa. So this is really, really soft material. The GECs have been used to build the perimeter dike, because this area was also influenced by the North Sea and by tidal ranges, and therefore the perimeter dike was built to then hydraulically fill the inner part of the area. To give you a nice idea how soft this material was, I show you this video sequence. I hope it runs smoothly at your end. And you really see nicely how easy the steel pipe can be brought into the soft soil, and shows you the soft conditions of the material. In the next video, we also see the parts when the encasement is withdrawn. And then you can see the head of the column, that it really has a nice shape, that it has an integrity, and that there is no material lost, even with such low lateral support from the soft soil. This is the cross-section of the perimeter dike, because they also had to tackle the challenges of extrusion and lateral my spotlight to extrusion and lateral deformations. The cross-section was made really with a wide base, really to enhance the overall stability and the safety against bearing failure and lateral displacement, as well as extrusion. The basal reinforcement which has been used was one layer of 1,000 kilonewtons and one layer of 500 kilonewtons, because this time, it was I think 15 years ago, the technique didn't allow the production of high strength materials higher than 1,000, but today we would really recommend to install one layer of 1,500 kilonewtons. This is one picture during construction. Because I told you this area was influenced by the tidal range, and therefore they really brought a lot of rigs during low tide to the site to install the columns in the dry. But they also used barges in areas with higher water level or in low tide. Gives you a nice aerial view about the size of this project and really the effort which was taken to install those columns in the working times they had available. And again, here we have some nice insights from the working mechanism. And this time I would like to show you the settlements over time after the handover. The dashed line you can see here, this is the settlement prediction at the very beginning based on conservative assumptions. And then based on measurement results we had, which is the black line, the continuous line, this prediction had to be corrected until the real results could be met. And this actually gave us the idea that we can assume that the creep settlements can be reduced by 75% by the system. And this, as you remember, we don't load the soft soil that much. We only, the main part of the load goes directly into the sand columns, and therefore the creep settlements resulting from the soft soil can be reduced significantly up to 75% in this project, which can be also for very sensitive structures like railway lines or abutments, which can be a very great advantage. And we're coming to the last case study I would like to present you today, and this is a project in Turkey. This is a construction of an up to 20-meter high embankment on 40-meter on soft soil. And the great challenge here that we had, or that the columns had to be installed in a water depth of up to 7 meters. So the length of the embankment, so the embankment was placed here, was 400 meters. And then Turkey is also a seismic active region, which resulted in the fact that we had to also consider seismic loads in the design, which brought us to very high grades for the basal reinforcement, 3 layers up to 1,600 kilonewtons. So this is the existing viaduct you have seen on the top view, and this is the place where the new embankment was played. So the big advantage here that they had a great sand source close by, literally in the neighborhood of this embankment, and therefore the geosynthetic encased system was used because they got the sand really without big effort and also for a very good pricing. So this could give the entire project a great benefit. This is a screenshot from the global design. So we use normally the stability, geostability software, but of course any kind of slope stability software can be used. Then in this case, you can see that also seismic load of 0.16 has been considered, and then the basal reinforcement strength can be increased until the required degree of utilization or factor of safety is met. And also what can be done is that geosynthetic encased columns are included so that you have the that you can consider or take into account the stability increasing effect of the columns itself. And this was then the final cross-section, the typical cross-section. You can see up to 40 meters, up to 22 meters high, 12-meter water depth in this case, and the basal reinforcement with 3 layers, and the GEC columns arranged in the triangular pattern with a spacing of 1.7 meters. The construction started from onshore with large boom cranes, but also with barges in some parts. There is online, so I have no time to show it you today, and I was afraid it doesn't work pretty well, but you can find it on YouTube. There's a nice animation of this project showing you the whole construction method they have been used. So very interesting to see as well. This leads me to my conclusion today. So the geosynthetic encased columns is a system comprising of granular columns encased with a sleeve with no seams, and the basal reinforcement high strength geosynthetic on top. And then we have the biggest benefits in extremely soft soils. So when normal stone columns will just fall apart, or you will need a lot of material for stone columns, for example, then the encasement ensures the integrity of the column. Therefore, we can conclude that the encasement can be used in extremely soft soils, even low to 1.5 kPa. And again, the encasement ensures the column's integrity and also the draining function, and avoids the loss of fill material. It provides an inwardly acting counterpressure, and it reduces and accelerates primary and secondary settlement. And we have also seen in the Hamburg case study that we even can reduce creep settlements. And compared to other systems like common stone columns, we can reduce the number of the columns because the geosynthetic encasement gives some extra support. Then the working mechanism, the settlements will be transformed into a lateral expansion and the activation of tensile forces in ring direction. And very importantly, it acts like a mega drain. So even we have settlements, the consolidation will happen very quick, and therefore we can, before we build our superstructures on top, we can compensate those settlements. Yeah, then we are coming to the question parts. I can also recommend you to check our homepage. You'll find very interesting videos there, case studies, video casts and tutorials for any kind of geosynthetic application, but also for the geosynthetic encased columns. Okay, thank you very much for your attention.
Thank you, madam. Before question answer session, I will share Google Form link. I request all the participants to copy Google Form link. So I request all the participants copy this Google Form link, and its purpose is sharing the PDF content of this lecture and your feedback. So now I request participants send their questions through chat. So madam, kindly observe the questions.
Excuse me?
You can observe the questions in the chat.
Yeah, I also have some questions privately. Shall I start with those?
So it is from a question from Ratnakar Mahajan. PET material is recommended for encased stone columns. However, Will PET not lose its strength when used in presence of seawater? Slide 23 shows some variation in load on column nearly at the end of the test. Why it is so?
Can you please repeat? So was in the presence of seawater, was it?
PET material is recommended for encased stone column. However, will PET not lose its strength when used in presence of seawater? Slide 23 shows some variation in load on column nearly at the end of the test. Why it is so?
Yeah, so the resistance against seawater can be tested and also has to be taken into account, of course. And this can be, so if this is really an issue, this can be then compensated by taking a higher strength of the material. But in generally, the polyester and also the PVA material is resistant in seawater.
Thank you, madam. Next question, the infill has to be sand only.
The fill can be sand, gravel, or also crushed rock. We only have to consider that crushed material can have a higher damage to the material, but this can be taken into account. And what we also have observed is that if you have uniformly distributed material, that you get a nicer, better compaction as compared to crushed material. But it can be used in general, everything can be used, but we just have to consider the damage of the material and also the load or the distribution of the material and the compactability. But normally with sand, gravel, or crushed stone, it works very well. We just need a permeable material. It doesn't work with any low permeable materials like silt or clay, because then we will lose the mega drain function.
Another question from Mr. Yogendra. Is there any case study or project reported in India?
As far as I know, we don't have case studies in India. Yeah, but the material was also installed in Brazil, and closer to here was Malaysia, and it's discussed very often also in Hong Kong and places with which are actively considering land reclamation projects. Then it comes up frequently.
So, madam, another question from Atnu Adhikari. You have mentioned about end bearing. How this is considered in design?
When the bottom varies?
You have mentioned about end bearing. How this is considered in design?
May I ask you to repeat this again? I'm so sorry, I cannot understand.
How this is considered in the design of end bearing? End bearing. Hello, madam.
Hello, can you maybe, it's written in the chat function, can I read it maybe?
And I will chart the same question, madam. And this is the question, madam.
Okay, thank you. Okay, so an end bearing layer, this is, so the design for the column is only made in the parts for the soft soil. So it assumed that the bearing, that the layer where the geosynthetics stands on is a bearing layer, and that means there are some, when we go back to the, can you still see the presentation? So there are some conditions. I think it's higher than 5 megapascal stiffness modulus, needs to be 10 times higher than the soft soil. and the friction angle of higher than 30 degrees. Then this is a bearing layer, and we don't consider this in the vertical design.
Madam, can you stop your share and so you can able to see your chart yourself so that it is easy. And you can keep chart in front of you by pop out so that it is easy for you. How many number of GECs can be installed per day with per rig? This is another question.
So this depends. Yeah, so very experienced contractors can do 3 to 4 columns per hour or even 5, but this is a learning curve. At the beginning, you will install less, but then if you find yourself in the process, then it's much easier. So then it can go up to 4 to 5 columns per hour per rig. So you have seen that in some projects they have worked with 2 rigs, but 1 rig, 4 columns per hour, this is a very good value. But at the beginning, it might be only 1 or only 2. But this is a learning curve, and you get easily arranged with everything.
Madam, can you start your video?
Excuse me?
Can you start your video? It is so that video?
Yeah.
Okay. And you can observe the questions. And there is another question from Vishnu Viredi. How working platform is made on very soft soils for mobilization of cranes for installing columns? Please explain.
Yeah, this is a very important question because the rig is also, and the cranes are very heavy, and this is can be a challenge. So normally you can build a working platform also with a geosynthetic reinforcement, so that you lay out a light geotextile and place a working platform and load it in end tipping method. And this can help you to bring the machinery on. And as soon as you have the first columns, your cranes and equipment can already drive on the columns. So they immediately can be used after installation. This is also a good benefit. So at the beginning, we would recommend a light geosynthetic as working platform reinforcement. And then the installation can be started.
So any questions, Mr. Please once again chart so that stone size above 60 mm is also recommended. So we had hard granite abundantly available. This is the question. Stone size above 60 mm is also recommended.
So the question is whether you can use granite to fill the column.
Yes.
Okay. Is it possible to break the granite in any particle size you want? So we can specify the particle size which would be most useful and which we expect to behave best. I think this could be done. But we have to be careful that the material like granite, that it can be rather sharp and edgy, but then also installation damage tests can be run to analyze the damage of the material. And maybe different grain sizes can be tested to have the best behavior.
Another question from Gitanjali, how to compact the stones without affecting the integrity of encased material?
Yeah, very good question. So the compaction of the column will happens firstly when the steel pipe is withdrawn. This happens under vibration, so there will be a compaction. And then we will compact the columns when we place our embankment. So this is a very important that you always have an embankment on top of your encasement to activate and to compact them. So this happens then during construction.
Madam, another question. If the geosynthetic gets clogged by the clayey type of material from the surrounding, how will the drainage be ensured on the external side?
So you mean that there will be a kind of smear zone at the outer part of the encasement? So what can be done is that we also can do filter stability analysis and then try to find whether the material is suitable or not. So this can be considered in the design. And there's also research about those smear zones, but in all projects we have made so far, it was not big, it was not a great issue.
So there is one question from Salman Jettar. Can we replace GEC with PVD? If yes, please can you add some points on advantages of GEC over PVD?
I think the PVDs is a great system if you want to accelerate consolidation and if you can allow for settlements. So the big advantages for the GECs compared to the PVDs is that you also can reduce settlements. So with PVDs, you cannot enhance the slope stability or you can also not reduce settlements. So this is what the GECs can do, that they're really load-bearing elements and that they can actively support your system. So anytime you need, if you have stability issues, if you have settlement issues, then the GEC is useful. Whenever you can allow settlements to happen and you have time for the consolidation, then PVD is the best system for you.
So there is another question from Priyadarshini Maniam Rajan. Do you have any instrumented data for pore pressure measurement?
Yeah, so pore water measurements can be analyzed and also really often are, because this is, for example, in some countries in Europe, it's mandatory to have the pore water pressure observed to know when you can add additional load to your embankments. So therefore, many construction sites, I know the pore water pressure is monitored with pressure cells, for example. This can be done.
What are the
But normally it's in the soft soil, not in the column itself, because there won't be any excess pore water pressure in the column.
So there is another question. What are the type of failure of GEC?
The type
of failure
of the column. So compared to common stone columns, you won't have buckling or bulging, because what happens when you overload a column? So when you put more load on the column, it will settle, and then the settlement will be transferred to the surrounding columns because it's an interactive field of columns, and therefore we won't have those kind of failures. So what still can be a problem is slope failure and lateral displacement, but this can be considered also with the use of the basal reinforcement and can be improved by the basal reinforcement.
Madam, one question from Narendra Samadhiya. How the compaction of granular material in encased column achieved? How the settlements measured?
Yeah, so the settlements, the compaction the first part will be during construction when the steel case encasement is withdrawn, and then by loading. the rest, so the required compaction will be done by loading. And second part of the question, I think it was how the settlement observed. Yeah, so normally the settlements will happen rather quickly in the transaction process.
How is different from GeoPeer system?
GeoPeers, I'm not, this is a sand column, is it right? I think the GeoPeers is a normal sand column without any encasement. And as far as I know, the sand column is only a drainage element. So this is similar to the question with the PVDs. So with sand columns, you have a soil replacement partly, but you don't have the improving effect of the encasement. So this is not, so a sand column is not typical bearing element, I would say. So this is the big benefit of the GECs, that you can load them and that you can really consider them as bearing elements. And whereas the sand column is more or less a drainage or a soil replacement element.
A question from Mr. Adarsh HS. What are the disadvantages of GEC?
Okay, this is a good question. The disadvantages, yes, it really depends on your construction site. So very often we have to consider all different kinds of conditions on your construction site. For example, if you don't have any granular material available, the GC system doesn't make any sense, because then you have to pay a lot of money to bring the granular material to site. This can be a disadvantage. But in other projects, you might have a sand source just in the neighborhood, and then it can also be, again, an advantage. Obviously, for most of the engineers is the cost, because they compare just cost of a column, GEC, compared with cost of a column encased normal stone column. And then you have the textile, which is additional cost. But if you look at it in the bigger picture, then you see that you also can reduce the number of columns. So the cost benefit might also balance in a way. So it really depends on your construction site. But if you are interested in using the encased columns, we can check the feasibility, and then we can say whenever it's feasible and beneficial and whenever not. And when the soil is not soft enough, let's say, so then it's really not easy to install the columns, and then you don't have a great benefit compared to normal stone columns. But if you have extremely soft soil, this is the big benefit of the columns, of the geosynthetic encased columns.
Madam, one more question. If sand is not available and stone is used as a fill material, and if it damages the encasement, in such case, we need to use encasement of higher strength. Won't it increase the cost of the project?
It can, yes. So higher strength material are normally more expensive than low strength material. But again, if you, for example, get the material for free because you maybe have sourced it from another construction site you just had, then it can also be a cost benefit again. So this really depends on your construction site. So you have to consider not only the cost of the textile, but also transport costs, workload costs, and also the benefits and safety of the system, so that you don't have any creep settlements. So in the long term, that you have maybe a nicer structure with less serviceability issues.
Madam, most of the questions were answered. So thank you, Madam.
Thank you very much.
For the excellent presentation and question answer session at the end. I am thankful to Madam and also the participants for actively participation in the question answer session. Thank you, one and all.
Thank you very much.
Thank you.
Thank you.